Hi folks, today we're going to do some simulation and analysis on the Vans RV-15 engineering prototype using the flight simulator X-Plane 11. The Vans RV-15 is a new aircraft design from Vans Aircraft, a kit plane manufacturer up in Aurora, Oregon. It's the company's first foray into a high-wing, short takeoff and landing design. It's currently flying in engineering prototype form, and they've been very clear that what they're flying right now doesn't necessarily represent the final production kit. Though I thought it would still be interesting to take a look at its handling and performance and compare it to some popular similar aircraft such as the Sling High Wing and the Glasair Sportsman. First off, let's talk about what went into making a sim model of the RV-15 and X-Plane. As with any computer model, there are assumptions that don't necessarily match reality. I made the best of the public information out there, including an excellent kit planes article, an AOPA article, and videos from the public of the aircraft at Oshkosh, as well as the information that Vans has published themselves. I've linked all this reference material in the description below if you want to read more on the aircraft's technical details. And if you don't care about the model making details, I've also put markers in so you can skip ahead if you want to what the performance is. So from these sources, we can piece together a pretty good model of the aircraft, starting with the power plant. From the Vans website, the prototype has a 220 horsepower Lycoming IO390 EXP-119 engine, swinging an 80-inch Hartzell prop. They do say that it is designed for Lycoming engines from 180 to 220 horsepower, but I went ahead and modeled the higher horsepower just to be optimistic, and it's better comparison to the other aircraft that we're looking at. For the wing, from the AOPA article, we get a 36-foot span, and from kit planes, about 170 square feet of wing area. It's a constant chord design, so this gives us a 4.7 foot chord along the span of the wing. The next question is the airfoil on that wing. From the CAD pictures in the kit planes article, it looks like the wing is close in profile to a NACA 2414. I used a NACA 2412, which I had data for readily available, and I think the performance is close enough with a Delta CL Max from that change in thickness of only 0.02. They do mention in that article that is a custom profile that was developed, not just a NACA, but it's kind of the closest I've got. So the ailerons and flaps are split approximately 60-40 along the span from the kit planes article. The flap has a deflection of up to 50 degrees with 10, 25, 40, and 50 degree settings according to the APA video. Both the ailerons and flaps are 30% chord, and the ailerons are 20 degree down and 15 degree up deflection. Just guessing from the photos. The all-moving horizontal stabilizer is roughly 10-foot span and 3.5-foot chord from matching photos, with a 20 degree down and 20 degree up deflection about the quarter chord, which was checked with the APA video. The vertical stabilizer has a 6-foot span with 4-foot root chord and 3-foot tip chord with a 6-degree sweep for a straight trailing edge. The rotor extends the length of the vertical stab and has a 20-degree deflection and 40% chord ratio. NACA 0009 airfoil was used for both the horizontal and vertical stabs, which appears to be close from the CAD imagery in the kit planes article. For the wing struts, I used a NACA 0009 as well, with a 9-inch chord strut at a 40-degree angle extending from the bottom of the fuselage. For the fuselage, I used a combination of the CAD image in the kit planes article and Cessna 180 side drawings from POHs. AOPA quoted the length as slightly less than a Cessna 180. I used a length of 24 feet from spinner to tail. The engine was given a 2-degree downward cant on the fuselage mounts to eliminate nose-up pitch with power, and a 2-degree side cant to minimize required rudder. The landing gear is a 30-degree angle legs with 26-inch diameter mains with a 9-inch diameter tail wheel. There are brakes on the 2 front wheels, and the tail wheel is cast ring. For weight and balance, the mid-CG is 7 feet from the nose, and that's the position I use for all the testing. I set the empty at 1150 pounds and a gross of 2050 per the kit planes article, with the current prototype gross weight limit and Vans target useful of 900 pounds. I set the maximum fuel load as 50 gallons / 335 pounds with 100 low load, and that's the fuel load that's estimated for the final, not what the prototype has with a 40-gallon cockpit tank. Once I had the sim model flying well with decent handling qualities and good control power across the envelope, the first thing I looked at was the stall speed and stall handling. At the maximum gross weight of 2,050 pounds, I used a Part 23 power of stall testing technique and found a zero thrust power setting of 38% at 1.1 the found VS. I think that's going to vary quite a bit to the final, given the details of how X-Plane rigs props and throttles compared to real life. Interestingly, the results show that the stall speed actually increased slightly at the higher flap settings. The lowest stall speed was 42.6 knots with 25 degrees of flaps, and it increased up to 45 to 46 knots at 40 to 50 degrees of flap. We did some quick research on this, and it appears from some old NASA papers that it's maybe a known phenomenon for foul flaps to run out of steam and start seeing diminishing returns of delta CL max above 30 to 40 degrees of deflection. I don't fully understand the error reason for this, other than maybe the flow over the flap itself separating prematurely at high deflection. Could also just be a sim error. I think it'd be interesting to see how this matches reality of what they get out of testing the aircraft. The slow flight handling in the sim also becomes noticeably worse at 40 and 50 degrees of flap deflection. Unlike at the lower settings where there's a clean brake / wing drop and good handling up to that point, the 40 to 50 degrees of flap involves a lot of buffet and sloppy handling up to the brake. It'll be interesting to see if Vans leaves this amount of flap deflection in or limits to something more around 25 to 35 degrees of flap deflection. For landing performance, I did some approaches with a 55 knot VREF using the Part 23 technique on a 3 degree slope. It's tricky to get solid distances in X-Plane as I don't have good braking control to stop noseovers with the tail wheel layout. Though it appears rollout distances of about 300 feet are possible with a 3-point landing, maybe closer to 600 feet with a wheel landing at max gross in zero wind. For takeoff performance, I did a survey of flap settings and rotate speeds initially to find the best technique. Not surprisingly, at rotate speeds at or above stall speed for a given flap setting, there's no tendency for it to stay on the ground. Lower rotate speed is better and more flap is better. For the Part 23 mins of a rotate at stall speed and a speed at 50 feet of more than 1.2 VS for a single engine, I've found the best performance is a 25 degree flap static takeoff, rotating at 42 and pitching at 15 degrees nose high or 51 knots through 50 feet AGL. This gives about a 380 foot ground segment and 675 total to 50 feet. For climb performance, first I surveyed to find VY. The climb performance curve is pretty flat, as to be expected for this kind of airplane, peaking at around 80 knots. At sea level, this gave a climb rate of 1,666 feet a minute. VX is much slower, around 50 knots from my testing. For cruise performance, I did testing from 75% power down to 20% at 8,000 feet MSL, standard day conditions at max gross weight. The results are shown in the plot. 151 knots true at 11 gallons an hour with 75% power for max speed, and if going for range, about 108 knots true at 4.7 gallons an hour with 30% power is best before efficiency drops off. Down low at sea level, standard day, a max of 155 indicated as possible at 94% power. It's a lot better cruise than Vans is advertising for the prototype, which is encouraging. I think they have their goal as greater than 140 knot cruise. When we put it all together, this is what a pattern in the RV-15 could look like. First, we take off by using a static technique, 25 degrees of flaps, and rotate at about 42 knots. Next, initially climbing slow at 51 knots to clear the obstacle, then increasing our speed to 80 knots, working out the flaps to climb to pattern. On downwind, we can roll the power back substantially, and then turn base to final at 65 knots, bring out the flaps at 25 degrees, then slow to 55 knots for final and touchdown. For an example of a mission that you could do in the RV-15, let's look at Palo Alto, California, up to some backcountry destination like Loon Creek in Idaho, sort of a two-person weekend getaway mission. Palo Alto is a reasonably short asphalt strip in the Bay Area at about 2,400 feet. But obviously no problem for the RV-15 departing, even at max gross with no wind. Then it's about 4.5 hours of flying and an econ cruise of 60% to get you up to Idaho with just over 2 hours of reserve fuel remaining. Landing up at Loon Creek with 1,200 feet of runway at 4,000 feet of elevation is no problem. The 900 pounds of useful load is enough that you can take 50 gallons of fuel and 2 adults with still plenty of weight left over for gear. And you'll get up there with enough fuel to get to an airport that has fuel on the way home, which is an important thing for a backcountry airplane. When compared to other aircraft in the class, the RV-15, if it can keep up the performance from the engineering prototype and production kits, does seem to have quite a competitive advantage. I looked at a few different aspects of performance for the RV, the Sling High Wing, and the Glasair Sportsman. To help simplify a comparison, I've color-coded it as green for good, orange for middle, and red for bad. You can see that the RV is clearly ahead in almost every category except for stall speed, where it is just behind the Glasair Sportsman from the testing I did. Now again, these are simulator numbers based on an engineering prototype, so it'll be interesting to see how the final product compares to these numbers. Also, with experimental kit-built airplanes, a lot of the performance is down to individual engine selection and build options and quality, so these numbers may vary quite a bit. But overall, the RV-15, especially given Van's popularity, does seem to have an edge. If you want to experiment with the flight model yourself, I've put a link to download in the description below, along with links to the references I used for this video. It's my first time trying out this idea of simulating a new aircraft design and X-plane, flying it and looking at performance for fun and learning, so, please let me know if you have any feedback in the comments. Cheers.